This is Chapter 9, Problem 13. In this problem, we have an object that's fired at 20 meters per second at an angle of 60 degrees with the horizontal, and then at the maximum height, it's going to explode into two pieces. We're going to start this problem looking at it through kinematics. We have a velocity of 20 meters per second at an angle of 60 degrees. We can break that down into an x and y component, as I've done below. We get a v naught x, an initial velocity in the x direction equal to 10 meters per second, and an initial velocity in the y direction equal to 17.32 meters per second. We're going to figure out the maximum height that the object reaches using the fact that the velocity in the y direction at maximum height is equal to 0. So we're going to have 0 is equal to 17.32 squared, that's the initial velocity in the y direction, plus 2 times the acceleration. Make sure to make that negative 9.8 meters per second squared times delta y. And we get a maximum height that the object will reach of 15.31 meters. So that's the max height we're going to reach. Now we want to figure out the time it takes to go up and come down. We know that if we're starting from maximum height, the object has to fall 15.31 meters, and its initial velocity in the y direction will be 0. Its acceleration in the y direction is negative 9.8 meters per second squared. So it's going to fall minus 15.31 meters is equal to 0. The initial velocity in the y direction as it falls to Earth is 0, plus 1/2 minus 9.8 times t squared, and we get a time in the air of 1.77 seconds. Remember, we're going to double this time to figure out the entire time that the object is in the air. It takes the same amount of time for the object to go up and come down if we are returning to the same vertical height from which we started. Now we can figure out the displacement in the x direction during this initial time period of 1.77 seconds, when the velocity was 10 meters per second. So delta x is equal to v naught xt plus 1/2 a xt squared. Notice that the acceleration in the x direction is 0. This is a basic kinematics review. So we have that delta x is equal to 10 multiplied by 1.77, and we get 17.7 meters for the first leg of the trip. Now, since the object explodes into two pieces, we're going to use conservation of momentum to figure out how fast the second piece is going. The pieces are 1/2 of each other after the explosion. The one has 0 velocity in the x direction since it drops straight back to the Earth. So using momentum conservation, P initial is equal to P final. The initial momentum in the x direction was the mass times 10, and that's now equal to, since only half of the mass continues to move forward in the x direction, 1/2 the mass multiplied by some final velocity squared, and we get that the final velocity in the x direction after the explosion is 20 meters per second. We now find the horizontal displacement during the second leg of the trip after the explosion by using the new velocity in the x direction, which is 20 meters per second. So 20 multiplied by, it's still in the air for the same amount of time because the y component of the velocity determines how long it's in the air. So we get a delta x for the second part of the trip equal to 20 times 1.77. And that is equal to 35.4 meters. 35.4 meters. Now we add the two legs of the trip to find the delta x total. That's going to be 35.4, there's my cat about ready to jump on me, plus 17.7, and we get a delta x total for the entire trip of 53.1 meters. So to recap, we used kinematics in the y direction to figure out the maximum height that we reach. We used the maximum height that we reach to figure out the time that it takes to reach max height. It's the same amount of time to reach max height as it is to fall to the ground. The explosion takes place at max height, so we're going to use the initial velocity in the x direction, which does not change, to figure out how far we go in the x direction while we get to max height. Then we have a conservation of momentum problem since the little piece explodes into two pieces. One drops straight down, so 0 velocity in the x direction. That means all the momentum goes into 1/2 m. We get a velocity of 20 meters per second. Use that and the time to figure out the second horizontal displacement, and then add the two together to get 53.1 meters.